In this tutorial, we will be discussing the mean free path, diffusion and effusion of gases in real gases. Molecules in a gas travel in a straight line until they collide with one another, with another molecule, or the container. So notice that all of these have straight lines until they bounce off of something. Then they follow in a straight line again. The average distance a molecule travels between collisions is called the mean free path. The mean free path decreases as the pressure increases. If we think about why the pressure increases, that would explain why the distance decreases. For instance, if we add more molecules to this, it has a higher likelihood of bouncing off another molecule quicker, and so the path would be decreased. Or perhaps the volume decreases, which means that it'll hit the sides more frequently. There are two terms that reflect this: diffusion and effusion. Diffusion is the process of collection of molecules spreading from a high concentration to a low concentration, where effusion is the process by which a collection of molecules escapes through a small hole into a vacuum, such as this. See, there's a small hole here and the gases are coming through one by one. Both the rates of diffusion and effusion of the gas are related to the root mean square average velocity, which is what we calculated when we were talking about the kinetic molecular theory. For gases at the same temperature, this means that the rate of the gas movement is inversely proportional to the square root of their molar mass. So we can use Graham's law of effusion to solve for this. For two different gases at the same temperature, the ratio of the rates of their effusion is given by this equation. So here's the ratio of the rate, the molar mass divided by the square root of the molar mass. Notice here, the gas of A over the rate of the gas of B is the molar mass of B divided by the molar mass of A. It's flip-flop from one side to the other. So we can calculate this by saying calculate the molar mass of a gas that effuses at a rate 0.462 times N2. So the rate of some unknown compound over the rate of N2 is going to be equal to 0.462. So we can then take this information and say 0.462 is equal to the square root. Now notice that nitrogen's on the bottom here, so we're going to put it on the top of the next one. 28.02 over the square root of whatever compound this is. Alright, so first thing I'm going to do is multiply and get that square root x on top. Now I'm going to get rid of the square root 28.02. 0.462 square root x is equal to 5.29. Now I want to get rid of the 0.462. So the square root of x is equal to 11.46. To get rid of the square root, we're going to square both sides. And that is x is equal to 131.3 grams per mole, or, because there's only three significant figures, 131 grams per mole. Let's try another one. Calculate the rate of effusion for oxygen to hydrogen. So the rate of oxygen over the rate of hydrogen, we're going to reverse the order over here. The square root of hydrogen over the square root of oxygen. So the square root of 2.02 over the square root of 32.0 is equal to 0.251. Now let's talk about ideal gases versus real gases. Real gases often do not behave like ideal gases at high pressure or low temperature. Notice here, this is the ideal gas. They're very close to it, but they are slightly off on occasion. The ideal gas laws assume that there's no attractions between the molecules and the gas molecules do not take up space, and this is based on the kinetic molecular theory. At low temperatures and high pressures, these assumptions become less valid. Because real molecules take up space, the molar volume of a real gas is larger than predicted by the ideal gas laws at high pressure. So as the pressure goes up, notice there's a deviation here. As the molecules are forced to have more pressure, they have to acknowledge the actual size of the molecule itself. And so there is a deviation in the molar volume is not exactly the same. At high pressure, the amount of space occupied by the molecules is a significant amount of the total volume. So the space that the molecules themselves take up actually count towards the volume, where the ideal gas laws don't count for that. The molecular volume makes the real volume larger than the ideal gas law would predict. So van der Waals modified the ideal gas equation to account for this molecular volume. And that's this part right here. Notice this is simply PV equals nRT. He added this extra bit here. B is called the van der Waals constant and is different than for every gas because their molecules are different sizes. Now let's talk about temperature. Because real molecules attract each other, the molar volume of a real gas is smaller than predicted by the ideal gas at low temperatures. At low temperature, the attractions between the molecules are more significant. The intermolecular attractions cause the real pressure to be less than the ideal gas law would predict. So van der Waals accounted for this as well with his modification of the ideal gas law. Once again, PV equals nRT right here, but look, he accounted for the volume here with this A, which is another van der Waals constant, and is different for every gas because their molecules have different strengths of attraction. N is still the mole, and V is still the volume. Combining the equations to account for the molecular volume and the intermolecular attractions, we get the following equation used for real gas laws, for real gases. So the pressure, notice the change in the volume here. That's because of the temperature issues. And then volume minus NB is accounting for changes in high pressure. And it still is equal to nRT. Over here on the right is the table of the van der Waals constants. Notice A and B. A is for temperature, B is for pressure changes. And every single one of these are different dependent on the amount of attraction. For instance, xenon has a higher attraction to other molecules than helium or neon, so its number is bigger. When we look over here, this is for accounting for the pressure. And because xenon is bigger, it has a higher number there. And that's an explanation of the real gas laws. Discard. Stop recording.